So today we're going to start 1.3. I did get an email from the course coordinator because of all the days off and delayed openings and everything this semester. They are going to push the test back, which is actually good. So what they're going to do is they're going to take a couple topics off the end of the course and just shift the whole schedule back. So as soon as I get the dates, I'll let you guys know, but that's actually good. So that means we don't have to like just cram it all in and haul ass. So we'll as soon as, like I said, as soon as I get those dates, but I think they're just going to shift everything back like a couple of days. So we'll I should know hopefully by Monday I can give you guys those topics or those dates. Sorry. All right. So today what we're going to do is we're going to talk about functions. And we're going to talk about domain and range. And the topic we're going to cover today is really important because you'll use it for the rest of the semester and even moving forward if you go on to calculus. Domain and range is something you're going to be expected to be able to do forever in math. So, and understanding what a function is something that you'll be expected to know. So it's pretty important idea. So we'll look at it. It's actually not too bad once you kind of get a handle on it. So first, let's define a function. So a function, right, from A to B, right, is a rule that assigns each element in A, and this is the important part, to exactly one element in B, okay? So when we're talking about a function from A to B, A is going to be the input variables, right? And B is going to represent the output variables. And it's important that you know that the things that go in can only return exactly one value, okay? So it's not the other way around. It's the things that go into the function, right? So let's talk about notation. So if you see y equals f of x, all right, x represents, in this case, the input variable. It's also referred to as the independent variable. So this is important vocabulary. So if you're reading a question and they refer to the independent variable, it's telling you it's the input variable, the thing that goes in. Y is going to be the output variable, and that's also called the dependent variable, right? So if you think about this in terms of just like everyday vernacular, right? If something's independent, it doesn't depend on anything else. It just kind of does what it wants, right? If something's dependent, then it's relying on something else. So this kind of makes sense. You pick the value of x first, right? Then you plug it into the equation or look at the table or whatever, however your function's defined, and then the output variable comes out. So the values of y depend on the values of x that you put in, okay? So, but x is completely independent because we choose it first, right? We read this as y as a function of x. So we could put any letter we wanted for y, right? The name of the function in this case is f, right? So when you see that notation, f parentheses variable, right? What's inside the parentheses is telling you that's the input variable. And then f represents just simply the name of the function. So we can name things h, g, x, it doesn't matter. F of x is usually the most common one used because f is for function. That's all it is, right? But if we're dealing with multiple equations, you'll see usually they'll kind of run down the alphabet. F of x, g of x, h of x, kind of like that, right? And then y, of course, represents the output. So if you're reading in a word problem, for example, and they say, well, express height as a function of time, well, of is parentheses, that right, multiply. So they're telling you time goes in and h is what comes out. So you have to be able to make sure that when you're creating an equation or you're writing a function that you understand what goes on the outside and what goes on the inside. there are three really common forms that you'll see a function expressed as. You could see it as on a table. We could see it written as an equation, or we could simply just give you a graph. So we're going to look at all three types, and then we're going to talk about domain and range, and we're going to see how do you find the domain and range when you're looking at functions of different types. All right, so for the first one, let's look at tables. All right, and so I want to look at two tables. All right, so we're going to write them down first, and then we'll compare them. So the values in this table are exactly the same, except I've switched the rows in each of these two tables, right? So the values on X in the first table are the values on Y in the second table, and vice versa. So the question is, what we want to know is, are either of these a function, okay? So the definition of the function is the input variable is only allowed to map to one output variable. So the way you figure out very quickly if you're looking at a table of values whether you're a function is you only need to scan the row of the input variable, and no value is allowed to appear twice, right? So if we look at this first one and we kind of scan across and look at these values, well, we see that we have 3 and 3. We also have 2 and 2. So what this is saying is 3 maps to 1, 3 maps to 4, right? And that violates the definition of a function. You can't have a value giving you 2 responses, okay? So if I asked you what's f of 3, you would come out with 2 answers. You could say 1 or 4. Well, that's not a function. If you plug in a variable, you should only get one value out, right? So the y values can be repeated, but the x values cannot. So no, right? Not a function, because 3 and 2 return more than one value. So we only had to look at the top row. When I switch the rows, however, and we look at the next one, well, x is 1, 2, 3, 4, 5, 6. That's a function because we only have the values in the x column, row appear one time each, right? And it's okay that if you ask f of 1 is 3 and f of 4 is also 3. It's okay if 2 different x values map to the same y. You just can't have the input variable returning 2 answers, okay? So this is a function. Right? Because each x value maps to exactly one y value. Oh, coffee. Keep losing my coffee. I need my coffee. So the other way we can look at things, we can say, well, we can look at a graph, right? So if you're looking at a graph, and we kind of took a sneak peek of this the other day, we can very easily test this definition. So what I'm going to do is we're going to draw 3 graphs. We're going to see if these are functions. And so I'm also going to give you the equations for these because this is kind of coming up soon. So if we want to test this definition of whether or not these are functions, all right? So remember, each x can only map to one y. So the way that we do this when we're looking at graphs is we apply what we call the vertical line test. All right, I want to use a more vibrant color. So the vertical line test says if I draw, right, a vertical line across this graph, it should only cross at one time, okay? And so if you imagine sliding this dotted line, right, back and forth across the graph, right, as long as you can't find anywhere that it crosses twice, then you're saying, well, each x value maps to one y value. So does anybody in here remember what the equation of a vertical line looks like? Remember what a horizontal line is? A horizontal line is like y equals some constant, right? And you get like a line with slope 0. So what's a vertical line? Okay, x equals a constant. So the reason the vertical line test works is because what we're doing is we're saying, well, we're saying x is that one value all the way across that line, and we're sliding it back and forth. So we're literally testing for that value x, does it return more than one y? And everywhere the line crosses the graph, that would be the value where it intersects that it's returning. So that's why this test would work. So all you have to do is just kind of scan across and just slide it back and forth. So this is clearly a function, right? Because it never intersects the graph more than once, right? If we look at this equation of a line here, well, clearly on the line, right, you can see that you slide, that's even more clear. You can slide it across and you can see that this is in fact a function. All right, but we kind of looked at this a little bit last week. I feel like it was like a year ago, right? When we talked about circles, well, I kind of gave you a little sneak peek and said, well, circles aren't functions, right? And semicircles are functions if they're the top or bottom half. But if you look at the right or left half of the semicircle, it's not going to be a function because it would fail the vertical line test. So here you can see that the only way this line would ever return exactly one value is if you drew it right here or you drew it right here. Okay, but everywhere else in between, it's crossing the graph twice. So no, because this fails the vertical line test. So I'm just going to abbreviate vertical line test as VLT from now on, just because we don't have to write that out every single time. All right, so the third form that you could see a function in would be an equation. That's very good. Can I move this? Okay. So if you're looking at a function in the form of an equation, and remember, we can name them anything we want. So the reason we don't always use like y equals every single time is like, what if I want to work with multiple equations? Well, if I define everything as y equals, then it's implied that those y values are the same. So then if you want to use y, then you got to start using subscripts like y1, y2, it gets really nasty. So this is why we just name functions using different letters. So that way we understand these are distinct relationships. So these are all equations of functions, okay? These are all equations of functions, and it's a little bit difficult just by looking at the raw equation to tell if something's a function or not. Now, by the time we get to the exam and we get a little bit further into the course, I would expect you to see these and be able to just look at them and tell me if they're functions or not. So there is a worksheet that I will be putting on ELC, not quite yet, but it's a list of graphs of basic functions you should know. So eventually you're going to be able to get to the point where you're going to look at that first one and you're going to go, oh, that's just a parabola shifted left 2 spaces, because we're actually going to talk about that. And then the next one you'd be like, oh, that's the square root of x shifted to the left 1. And then the absolute value, we would know visually what the absolute value looks like. So if you're not quite sure and you can't just picture it in your head, well then what we typically do if we're not sure and we look at an equation is we graph it and then we look at the graph, okay? So eventually you're going to be able to draw all of these on your own. But if I graph them, this is a parabola shifted up 2 spaces, so its intercept is 0, 2. This is the graph of the square root of x shifted to the left 1. And the absolute value of x looks like this. And obviously, this is the origin, and I'll label this intercept, right? This is 0, 1. So one of the things you can do to aid yourself in graphing is you can solve for the intercepts, plot those, and then if you know the like basic form of the graph, we can connect those dots. So if we look at these three graphs, well, all three of them pass the vertical line test. So all three of these are functions, right? And generally, if we give it to you in an equation like this, it's probably going to be a function unless it's like a circle. Like it's going to be something you know, and you should know circles are not functions, okay? So if we like to deal with equations, a lot, well, one of the things we like to look at is we need to know, well, what are the domain and range? So what are the acceptable values that are allowed to go in, and what y values will come out of that function, right? So there's two ways you need to think about domain and range. The first is the pure mathematical way, which is how I'm going to show you how to find that. The second is, well, even though in pure math terms you might calculate the domain and range for the equation and you might be mathematically correct, if you're working with a word problem, context matters. So if I gave you the equation of a line that maps your, let's say, blood alcohol level, right? So it says if you drink X number of drinks, right, your blood alcohol level measures this. Well, if you look at the equation, it just looks like a line. You might say the domain is all reals because the domain of a line is all reals. I mean, you look at the plot of a line, you're like every X value goes in, every Y value comes out. However, that wouldn't be true in an applied setting because your blood alcohol level can never be negative. It's 0, either it's in your blood or it's not in your blood. So you would have to adjust the domain in that case to say, oh, well, the domain is only going to be 0 to positive infinity. If we're doing a problem where we're calculating area and I give you a formula that returns, let's say, the length of a rectangle, well, then if the formula will accept negative values, the domain you would give for the problem that you're working, you would have to exclude negative values because we don't have negative lengths. So when you're doing a word problem and you're finding domain and range, if you do the pure mathematical way, that's fine, but then you need to go back and check for context. Do negative numbers make sense? Does 0 make sense? And you can knock out numbers that don't make sense in the context of the problem. So there's no real official term for that, but I've heard some people refer to it as applied domain, and I actually like that because it means in this application, this would be the actual domain. Does that make sense? So especially if you ever go on to take a stat course and you do linear regression, one of the things you always want to check for is, does the intercept make sense, right? Because a lot of times your y-intercepts are negative. Well, do negative numbers actually make sense in the context of this problem, right?
Will we ever have to exclude positive integers if it's not realistic? Like a human can be 10,000 pounds?
Maybe, yeah. I mean, probably not in here, but yeah, no, absolutely. Like there are upper limits where things just get ridiculous, but you would know from the context of the problem, yeah. So like let's say you're doing something in like biology and you're studying a chemical and you want to look at people's reaction to this particular chemical, but yet you know that it's lethal at a certain dose, well then obviously anything beyond that range is moot because nobody would be alive to study. So so there could be an upper limit in an applied setting, yeah. It's a good question. All right, so domain and range, let's define them. So this is a topic that I personally, when I first started learning this in like algebra class, did not get it at all. Like I understood the domain were the inputs, I understood the range were the outputs. I could look at a graph and tell you what was going on. Algebraically, I was getting the answer right about 85% of the time, but I had no idea what I was doing and why. And then one day it just clicked and I was like, oh, this really is easy, all right? So people just tend to overcomplicate this in their own brains. So first, let's define, right? Domain are all values of the input variable that the function will accept. So it's every value of x, let's say, that you are allowed to plug into the equation. So for example, if I had the square root of x, can't plug negatives under a square root, right? So we would not allow negative numbers to go in. So it's got to actually return a value for it to be allowed to go in, right? The range is all values of the output variable the function returns. So if I say, what is the value of f of x when x is 2, well then you have to make sure 2's in the domain before you can plug it in, right? If I say, when will a function equal 2, well then I'm saying when is the y value 2, and you would return the x value. So that value 2 needs to be in the range of the function, or you're not going to get a corresponding x. All right, so one of the things you want to remember is most of the things we work with in here are going to be numbers, but functions don't have to be numerical. They could be symbols. They could be words. We actually use this in statistics a lot. So if I'm testing colors of a car, right? Well, then all the colors that people name on the survey, those would be the range, right? And then all the question I ask might have to do with the input. So we could actually have symbols, and it is a function as long as everything that goes in maps to only one value coming out, right? So there's a couple different ways we can test for domain and range since we have 3 different forms of functions, right? So for tables are discrete values, right? So if you were to plot the values that you see on a table, what it would look like is just points on the plot. Those points would not be connected because the table's only telling you the values at those particular inputs. So let's go back and look at the tables we had before. Oops, this should be a 3. Yep, then a 2, then a 4, then a 3, then a 6, then a 2. And we'll go ahead and okay. So these are the same 2 tables we looked at before. So we know that table 1, the first table, is not a function. We've already just said that that's not a function because 3 and 2 appear twice, right? But if I wanted to list out the domain and range, right, on tables, right, we don't use interval notation, which we'll get into in a minute. We actually use set notation, right? So with sets, these are just a list of discrete values. So if you didn't know that this wasn't a function, and I asked you for the domain, what you typically do is it's going to return a list of values. We like to write them in sequential order, and we don't repeat numbers. So if I were to write the values that go into this non-function, right, we would write it like this. It would just be it accepts 2, it accepts 3, it accepts 4, and 6. And we don't write 2 twice, and we don't write 3 twice. Okay? If you look at the range, well, the range, right, is just 1, 2, 3, 4, 5, 6. So these brackets are curly. Those curly brackets mean set. For the next one, well, since all we did was swap the rows, the domain and range trade. And so on the range, right? And so to be kind of, it's more like a grammatically correct. You want to list them in sequential order and you don't want to repeat. Right? So it should make sense that if you plotted this and all you saw were dots, then it should make sense that the domain and range should just look like a list of things. Because if all you see are plot points on the, like a scatter plot, then all you're gonna see in the domain and range are just distinct values. You don't have anything to connect the dots, so you can't accept any intermediary values into this function, right? And if I asked you what f of, let's say 7 was here, well, you couldn't tell me. It's not on the table, and you don't have an equation or anything to go by. Okay, so you can't plug anything in here that's not on the table, and nothing's gonna come out of the function that's not on the table, right? So graphically, right? Graphically, we can find the domain and range by reading the graph. So for the domain, you read the graph from left to right, right? And the reason we go from left to right is the domain are the x values and the x-axis goes from left to right. So we want to make sure that we're just grabbing the values of x that go into the function. For the range, you read the graph from bottom to top. Can't write today. And the same reason, right? The y-axis runs vertically. So the reason you want to go left to right is because you want to write your domain and range in order. So you want to start at the negative x-axis and go to the positive x-axis. Then you want to start at the negative y-axis and go to the positive y-axis, right? The values in the domain and range, they're not lists anymore. They're given in what we call interval notation. And so what interval notation is saying, well, anything in this interval is allowed. So every intermediary value. And so because the graph is going to be like a solid line for those values, like it could be, well, it'll accept 3, it'll accept 3.23, it'll accept 5.25. So writing an interval notation, what you're really doing is you're grabbing the endpoints and you're saying everything in between is going to be okay, right? So the issue, though, is how to deal with the endpoints. So we use parentheses for endpoints that are not included, and we use square brackets for endpoints that are included. And we're going to do a couple of examples, and you'll see that we can use combinations of square brackets and parentheses, okay? Now, one thing to know, oops. Always use parentheses around infinity. It's not finite. No one knows where it ends, and if you can figure it out, then you'll be a millionaire. Probably a quadrillionaire, because no one's figured it out yet, right? So if you see if you want to use infinity as one of your endpoints, right, then you have to put parentheses around it. You can't put a bracket because it's not a fixed point you can stop at. So it's always going to have a parenthesis around there. All right, so let's look at a couple of examples of how to read the graph. So I'm putting a solid dot here, that's on purpose. And then I have an open circle here, that is also on purpose. Then this is an open circle. And so this is at 2. This is -5. This is -1. We'll say this is -1. This is -2.
What are the open circles mean?
I'm about to explain it, yeah. So I just want you to know those are open and closed. So this is where, when you're reading these graphs, and this will be something you will do you'll have to deal with stuff like this in Calc 1 when you get to things like limits. You're going to have to make sure you can read funky little graphs like this, okay? So just so you can kind of know on purpose, the top of this little curve does line up with the 2, okay? Just so we can make sure we're reading this right. So if I want to get the domain and range of this, For the domain, I read the graph from left to right, and I only look where does the function exist. So there's nothing happening past -5 over here, right? So the first thing I get to is -5 and the graph starts. Notice the dot is closed. That means the graph exists at that point. There is a point there, okay? So it starts with an x value of -5, so I have to use a square bracket, right? Then I come over to -1 and there's a gap between -1 and 0. But at -1, there's an open circle. So what that means is the function goes all the way to that value, but it doesn't exist at that point. So it goes up to, but not including -1. So you can't actually plug -1 into this function. So there's a solid line here, right, from -5 to -1, but I have to put parentheses around the -1. So any value between -5 to -1 will return a y value except at -1. There's there's a hole there. You can think of it like a pothole. So then in the x direction, we have a little bit of a gap. And then when x equals 0, right, it starts over again, but there's an open circle there. So what we do is we need to start a new interval for the second piece of the graph. So what we do is we use this u, that means union, right? Then because there's an open circle there, I have to put a parentheses around that 0, right? Then notice how the line, right, there's not a dot at the end of that line. That's implying that that line's just going to go on forever in that direction. But if you see like a solid endpoint there, then we know that graph would cut off, and we would cut it off at that point. If you saw an open circle right at this line, then we know that this would cut off. But this is just implying that this goes on forever, and so we can see if we're reading the x-axis, well then that implies it goes on all the way to infinity. So we would say the domain goes on to infinity, and we would put parentheses around that. So if you look at this example, you can see we can use a combination of square brackets and parentheses. Notice too that in the domain, those are all x values. So this is telling you all the values of x you're allowed to plug into this function. Now if we want to read the range, right, we want to go from bottom up. So the lowest point on the graph is actually right here, and that's supposed to correlate with -2. It's a solid dot, so it does exist there. Then we go up, and the peak here, right, the peak top of this graph, right, is at 2. And even though it doesn't exist at 2 here, it does exist at 2 there. So we include it in the domain. We don't have to break it off. Then from 2 to positive infinity, right, it's existing in all the y values. So this is just going to be -2 to positive infinity.
I thought you said it does exist, like, I thought if it exists, like at an endpoint, isn't there, don't you cut it off, when you cut it off at 2 for the first
Well, you would theoretically, right? But then this graph picks up at 2 and continues on. And so even though it doesn't exist at 2 right here, it does exist at 2 right there. So it does return a value 2. So if I asked you, when does this graph equal 2? Well, if you go up to the y value of 2 and draw across, well, it equals 2 right there, right? I just didn't label what the corresponding x value is that returns 2. So you want to make sure. Now, if I had lowered this guy down a little bit, like, or let's say I raised this up. Let's say this point started up at 3. Then I would have stopped the range at 2 and picked it back up at 3 and took it to positive infinity, okay? So you want to make sure when you're reading and you feel like there's a gap, you know, like I said in this case, especially with range, ask yourself the question, does the function ever equal 2? It actually does equal 2, so we have to include it in the domain.
And you would have used a union again?
Range. We would have used a union. You always use a union between intervals, yeah. So this is telling you that we can, for any value in here, I can say for what value x does the function equal 6? Well, then there is a value y equals 6, and you can find the corresponding x. All right, so let's look at another one. So one of the things that should happen when you look at your graphs, like I said too, is check those endpoints, because it can be a little tricky, but most people have gotten really good when they're asking you to do domain and range quantity. They well define the endpoints, and if the endpoints are not well defined, there's not an open circle or a dot, you get to assume that the function's going on forever in that direction. So in this case, right, even though the graph is turning upward, right, it's still doing kind of this if you were to like zoom out. So if we looked at the domain, we have no reason to believe that it doesn't continue on to negative infinity. So if I'm reading it from left to right. But then when I get to x equals 0, there's a hole there. There is no value that works at 0. So we have to stop it at 0, not include it. Then we pick it back up at 0 and take it to positive infinity. So another way of expressing this particular domain is all reals except 0. Because 0 is the only value of x you can't plug in. Right? The range, we start from the bottom and read up. So this is clearly going down to negative infinity in the y direction. But the y coordinate of this point, or non-existent point, was 1. So the range goes up to 1. It's not included because there's no actual value there. And then it picks back up at 1 and goes to positive infinity. So the range of this function are all real numbers except 1.
But if that was like a filled circle, it
would just be all reals. Yeah. So if you just had the graph of just a line, no breaks, no holes, no nothing, all reals. The domain is all reals, the range is all reals. Because it goes from negative infinity to positive infinity in both directions. All right, so tables, very visual, graphs, visual, okay? The tricky part is, how do you find the domain when you're dealing with an equation? So as of right now, we're pretty much only going to ask you to find the domain of an equation, okay? If you want to get the range, there is no kind of, there'll be some tricks later we'll learn down the road about, there's some techniques we can do if there's certain types of functions to get the range algebraically. But typically, if you want the range, you graph the function and you look at it, okay? But if you want to find the domain, for equations, well, it's impossible to test for every single possible value of x, right? There's infinitely many of them on the number line. So what we do is we look for values to exclude, and then accept everything else. So there are certain tells in the equation that set off kind of triggers algebraically for you to go, oh, we might have a problem here, okay? And the nice thing is there's only 3 of them, right? And the even nicer thing for you guys is you only have to worry about 2 of them right now, okay? So these are the only, but I'm going to give you the complete list because I want you to see there's the only 3 things you have to look for, and this list is never going to change, okay? So for the domain, you want to check 3 things, okay? The first is you can have no zeros in the denominator. So you'll know to check for that if you see a rational expression or a fraction, okay? Now this doesn't mean you can never plug x equals 0 into the denominator. It means whatever expression is in the denominator cannot equal 0. So we're actually going to do some examples where I'm going to show you how to apply these. All right, the second thing you have to look out for is no negatives under even roots. So what you're looking for here are equations with radicals in them or fractional exponents, because fractional exponents, which we'll see a little later, are another way of writing a radical, right? If you see x to the 1/2, that is the same thing as saying the square root of x, okay? But it's even roots. You cannot take the square root of -1, but you can take the cube root of -1. So if you're dealing with an odd root, this rule doesn't apply because you can have negatives under odd roots. You just can't have negatives under even roots, okay? And then the third rule, which we're just going to put little asterisks because this will come into play in Unit 2, but only positives inside logs. So when I say only positives, remember on the number line, 0 is neutral. It is not positive or negative. So if we say only positive values, that means no negatives, no zeros. Okay? Because 0 is neither. All right, and remember that these rules can be combined. Okay? So let's look at an example. If f of x equals 1 over 2x plus 1, and I want to find the domain of this, well, I see a fraction, there's no radicals, there's no logs, so I really only have to deal with rule number 1, right? Rule number 1 says denominator cannot be 0. So you take the entire expression in the denominator, and that's what that says. 2x plus 1 cannot equal 0. And then we're going to solve this for x. So that means that 2x cannot be -1 and x cannot be -1/2. So all that, when we say not equals, you just treat it like an equal sign when you're doing the algebra, right? And so that's telling me, all right, x is not allowed to be 1/2. So writing the domain in interval notation off of this stuff can be difficult for people. So you can add one more intermediary step to add a visual component for yourself. And what you do is simply draw the number line and sketch what the results of the equation told you. Because sometimes if you have multiple steps to pick, you might have to plot multiple things on your number line. So there's -1, or -1/2, excuse me. And what we do is we use an open circle because we're saying it's not allowed to be that value, but we get to assume that everything else works. So if I want to write my domain in interval notation, now I simply read the number line from left to right. So this will be -∞ to -1/2 not included, and then it picks back up at 1/2 and goes to positive infinity. So now if I said in words to you, well, the domain is all real numbers except for 1/2, if you look at that number line, that's perfectly obvious because that's what we did. We shaded every value on the number line except for 1/2. All right, so let's look at this. The square root of x plus 7. So the rule for radicals says, well, you can't have any negative expressions under an even root. So once again, remember, 0 is not negative or positive. So if I say no negatives, then that means as long as it's positive or 0, it's okay. So what we do is we say, well, I take the entire expression that's under the radical, and I say, well, this has to be greater than or equal to 0. So then we solve for x. So remember, with inequalities, as long as you don't multiply or divide by a negative number, you treat it just like an equals sign when you're doing the algebra. So x must be greater than or equal to -7. So if I sketch a number line, here's -7. It is allowed to equal -7, so I'm going to shade that in, right? But now this is saying x is greater than or equal to that value, so greater than means, right, we're going to shade to the right because those numbers are the bigger numbers. So the domain, if I read this, is -7 is included up to infinity and that would be the domain. All right. So let's look at one more. One over the square root of 5x plus 2. Sorry, that's supposed to be a 5. All right. So this actually invokes rule number 1 and rule number 2. So it's okay to have 0 in a radical, but not if that radical's in the denominator. So now 0 is off the table. So just like I did in the previous problem, I'm going to take the entire expression under the radical, and rather than saying it's greater than or equal to 0, now I have to say, well, it's only allowed to be greater than 0. It's not allowed to equal 0 anymore, because that then violates rule number 1, right? So now we solve for x. So 5x is greater than negative 2, and x is greater than negative 2/5. So if I draw my number line, there's negative 2/5. I am not allowed to include that value. And this says, well, all values greater are okay. So the domain is negative 2/5 not included to positive infinity. So then hopefully you can kind of see a little foreshadowing here when we get into unit 2 and we start working with logs. Domain and range is going to come back up again, and you'll see that we have another restriction that we'll have to apply that we have to check. But those are the only 3 things. There's never anything added to the list, and I don't care how many math classes you take, those are the 3 algebra tells. So you look for fractions, you look for radicals, you look for logs. You just won't see any logs yet, right? But any questions? Yeah.
I don't get the under even roots, because we had the, like in the second example, when it was the square root of x plus 7.
It's okay, so it's not the number, it's not what the expression inside the radical that makes it odd or even.
Okay.
It's the number in front of the radical. So if you don't remember when you started learning radicals, there is no 2 in front of a square root, right? So there's an implied, right? If I have the square root of x, there's actually an implied 2 there. So if I were to write this as a fractional exponent, it's x to the 1/2.
Okay.
But if I said x to the 1/3, that's the cube root of x. And so whenever you see a radical with nothing in front, it's just implied that it's a square root, right?
Okay.
But the reason for even roots is in order to pull a number out of a root, right? If you want to take the square root of 4, for example, well, you needed 2 2's to pull out 1 2, right? But the cube root of 8, you have 3 2's to pull out 1, right? So with a 4th root, let's say 4th root of 16, well, you need 4 2's to pull out a 2. So the reason you can't have negatives under even roots is you're always pulling out even combinations of things, and -1 times -1 would always be like +1. So that's why you can't have negatives, but a cube root of -1 is just -1, because it's -1 times -1 times -1, which makes it negative again. So that's why we just say even roots, right? So whenever you're doing a problem and there's an even root, you have to check the domain. If it's odd, you're good.
Okay.
You can plug in anything, okay? All right, cool. So we'll call it there.